Welcome back. I'm Professor John Gallaugher, and this is the solution video for questions 5 through 8 of our 2.5-hour physical computing midterm. Now, these questions focus on coding CircuitPython on the Arduino Nano RP2040 Connect, while the first 4 questions focused on CircuitPython using the Circuit Playground Bluefruit. Feel free to check out the earlier video if you want to see the CPB challenges. Also, feel free to see the previous video if you want to know how I set up this test, my approach toward grading in a way that encourages rather than discourages students to conquer tech challenges. But now, let's get right into question 5. And by the way, I usually set up questions so that they start out easier and then they get more challenging. So this first one detects gestures and plays sounds. Now this is identical to an earlier YouTube video where our students learned to use the APDS9960 breakout board to detect gestures. We're just changing the sounds here. When the program first runs, the sound "Don't Forget to Breathe" should play. This just indicates that things are running in our code. When a right gesture is detected, we should play the sound "wax on," and the lights in the Neopixel strip should light up in red from 0 to 29, and a left gesture should say "wax off" with the lights lighting up from 29 to 0 in blue, and we wait 5/100ths of a second between each individual LED light turning on. The video at the right shows how the build should work. The gesture sensor is imperfect. It doesn't always detect a gesture, but it does work with slow directional swipes. So let's take a look at a solution. Now, the modules we import are the usual suspects, but our students also know from previous code experience working with this gesture sensor that they need to import APDS9960 in all caps from the Adafruit _APDS9960.APDS9960 library. So they've done that before. Hopefully that was in their notes, or they knew to do that. Then using the STEMMA QT version of the sensor, they know how to wire that up as well. They're going to breadboard that to the Arduino Nano. Then to set up the sensor, we first create an I2C object. We're going to call that I2C. Then we create an APDS9960 object. We do that simply by passing in the I2C object that we created in the line above. And we could call this anything we want, but we use the name multi_sensor, or at least we did in our learning video. Multi-sensor is a good name because this can detect not only gestures, but also proximity and even colors. Now, to get the sensor to work for gesture detection, we set the enable_proximity property and the enable_gesture property for that sensor we just created, both to true. And that's it. It's just these 4 lines of code to set things up. And then here's the standard code for working with a Neopixel strip wired to the Arduino Nano. Our students have already done this in earlier CircuitPython school exercises. Students were also asked to use D7 as the data or control pin for the strip, and also to call the strip strip. Then we set up 3 colors that we're going to be using, and we turn off all colors on the light strip when we start. Now, the next code is used for setting up audio. Again, our students have done this before. The students were specifically asked to use D4 for audio out. That was on the standard slide earlier on. There are 3 WAV files that are in a folder called Karate, all in lowercase, so that should have been copied over to their Arduino Nano, so those files are there ready to play. Now, the play_sound function is a standard function that we've been using in class. It really functions like a reusable software Lego, so you can use this if you set up your audio properly. Anytime you want to play a file, you just pass in the string that's the exact name of the sound you want to play, and as long as your path also represents the directory or the folder on your device where those sound files are stored, you should be good to go. Now, in this line here, this is where we play that "Don't Forget to Breathe" sound when we start up our microcontroller. And then in while true, we get the gesture from the multi-sensor gesture object that we created, and we get that using the .gesture method. This is a method, so you've got to remember to add the parentheses at the end. We're going to store that in a value called gesture, and it's going to be an integer value. Now, in our example, we want to look for left, which is a 3, and right, which is a 4. Again, our students have already done this in earlier exercises. If we detect a left gesture, then we print that out. We actually didn't have to print it out, but again, this is a really good idea because it helps you demonstrate by looking in the console if your code is working properly. Then we play the wax off sound, and then we run through a loop in reverse. So we start at 29, and then we go down 2, but we don't reach 0, so that's what the -1 is in here. And then the next -1 means we're going to be counting backwards starting at 29. Then this command here will light up each increment value in the color blue, or each LED corresponding to the increment value in blue. We sleep for 5/100ths of a second. We repeat that 30 times, and then when we're done going through the loop and lighting all of the LEDs up, we wait for 1 second and then turn everything off. Now, if we detect a right gesture, that's gesture value number 4, we do the exact same thing. The only thing that's different is our loop goes in a range from 30. That'll go from 0 to 29. And that's it. Hopefully this worked out well. If not, hopefully you get it now. And if you did struggle, hopefully you can go through these solutions and it'll help you recalibrate your study and prep habits so that you'll do really well on the final exam. And hopefully that'll also strengthen your knowledge for your 3 upcoming projects that you're going to be working on. Next up is a capacitive touch drum machine using the 12-pad Stemma QT Gator board. That's the MPR121. Now, students have already used this in class to turn on different Neopixel colors depending on the pad that was touched. They've also worked with playing sound, so this question just combines those 2 things, touch and sound play. It's pretty straightforward. Students were also told where they can find a folder that contains the 12 drum sounds that they should be used. This entire folder should be copied over to the Arduino Nano RP2040. Also, if you don't know who this is Jizza, or also known as the Genius from the Wu-Tang Clan. He is a big advocate for STEM education. And yes, I know Blinka, the CircuitPython mascot, is quoting an LL Cool J lyric, not a Wu-Tang lyric. Don't get all up in my grill about that. So here's a quick demo of how a functioning build should work. And here's the solution code. So in addition to importing the usual suspects, you should import Adafruit_MPR121. That's what we need for our 12-pad Gator board. Now this is the code that we've already set up to play audio. As instructed on the setup slide, audio out is through pin D4. Now there are many different ways to set up audio files to play, but I think this one is fairly efficient and it's one that my students learned. We're going to create a list of all sounds, and it's just a list of the different strings that have the different sound names, 1 per pad that a person would touch when using this build. So this can be done with a single line like you see here, where the entire list is set up as a bunch of strings in between square brackets. That's in the comment. But I've also done this down here just to show you another technique. We create an initially empty list called sounds, but then we loop through elements from 0 to 11, so that's what range 12 does, and we create a sounds string, which is just the string sound, plus the number added to it for all of those sounds 0 through 11. And we add .wave at the end because each of these sound files ends in .wave. So that string is just created using this fstring statement here, and it's appended to our initially empty string. So when we've gone through this 12 times, we're going to have this same long list built up. We just built it up through a loop instead of having to put everything on one line. And if you're not exactly sure what this does, remember you can add print statements into this code to see, what actually is being created in here in this fstring portion, if that helps you figure things out. Now the path where we can find our sound files is 12_drum_sounds. That whole folder should have been downloaded and copied over to the Arduino Nano. And here's how we set up the MPR121 sensor over I2C. So we create I2C, we pass that into MPR121 to create an MPR121 object. I call my object touch_pad. This is our familiar play sound function, which we've already used. And in our while true loop, the way that we detect to see if a pad on touch_sensor has been pressed is we loop through a for loop 12 times, looking at numbers 0 through 11. And the touchpad MPR121 object that we created above actually is a collection of 12 different elements. Each one is numbered from 0 through 11, so each one can be accessed through square brackets. And the dot value property of each of those individual elements will be true if that particular pad is being touched. And if it is being touched, we simply play the sound using play sound, passing in the I value, which is the same as the sensor that's been touched, so we can play the sound file for that number. Now, by the way, you might have noticed that it's also possible to turn this here into a simple string and avoid having to create a list of sounds. That might be a fun exercise for you to try on your own. So in here, instead of referring to the list value, we could simply take the fstring value that we have up here, put that in, which will create a string that we can use to play a sound that we pass into the play sound function, and this way you wouldn't even have to create the sounds list. Either approach is fine. You might even have used a different approach. That's it for question number 6. Hopefully you got it, but if not, hopefully you see lots of different ways you could solve this problem. Now for this next question, we work with the VL53L1X distance sensor. So unlike the proximity sensor, the multi-sensor that we worked with, this distance sensor can tell us a precise distance. Those distances are measured in centimeters. Now we also work with a servo, and the idea is that when the distance sensor is within 30 centimeters or less, then the servo will rotate to 90 degrees. So if you have the back off sign attached to it, it will say back off. And if the sensor detects readings further away than 30 centimeters, the servo will return to the 0 degree position. And here's how we code it up. So in addition to importing board and time, we also import Adafruit underscore VL53L1X, which is the name of the sensor, and also PWMIO, which we need to work with our motors. Also, when we work with our servo motor, we're going to import servo from Adafruit underscore motor, and the VL53L1X is an I2C device, so we create an I2C object as we have previously, and we pass that into the VL53L1X class to create an object. We're going to call that object distance underscore sensor, and then we call the start ranging method. See how we have parentheses afterward? It is a method, and that's going to start our sensor so that we can begin to check its readings. Now here's how we set up a servo. We've done this in CircuitPython school before. Students in an earlier slide were told to set up the servo control pin as pin D5. We call this servo underscore 1, and it's up to you to see if you need a min underscore pulse or a max underscore pulse to calibrate your servo. You might need one or the other or neither of these. It's totally okay if you didn't need any. On the particular servo I was using, I set my max pulse to 2500. That just made sure that the arm could sweep out to a full 180 degrees. So again, if your servo was performing differently, you might have used different min or max pulse values, or you might not have used any of them at all. Now we also set the servo underscore 1's angle property to 0, so that we start out at the neutral position, so that's sort of flat or horizontal. If we put the horn in at that level, we've got the arm that's going to be pointing sort of out to the side, not straight up. And then in the while true loop, what we do is we make sure that the distance sensor is ready for the next reading by checking the sensor's data underscore ready property. That's going to be either true or false. If it's true, we go down here and we get the distance reading, and we put it in a variable called distance. And this particular sensor reports distance readings in centimeters. Now, we actually didn't need to create a separate variable for this, but it just makes our code a little bit easier to read because we can just refer to distance instead of this longer expression here. Now here, I print out the distance reading in centimeters and inches. Again, there was no need to do this. I didn't ask you to do this as part of the question, but it's a smart thing to do just to make sure that everything is working and you're getting your readings as expected. Now, if the distance is less than or equal to 30, this is where we set our servo angle to 90 degrees so that the little arm will pop straight up. Otherwise, we set the servo angle back to 0 degrees so it's horizontal. Then finally, we call the clear underscore interrupt method with 2 parentheses after this, just so that we can prepare the servo for the next reading, and we wait 0.2 of a second between readings. We slow things down, which is useful to do whenever you're printing things out to the console. This wasn't a vital thing to include, but that's it. So we worked with a distance sensor, we got readings, we responded by controlling a servo motor based on those readings. Hopefully that went well for you too. Finally, the noisiest challenge on the exam. This had students use the proximity sensor, a potentiometer, and a speaker to create a pseudo-theremin. Now, a theremin is an instrument that you do not touch. For example, if you've ever heard the old Beach Boys song, Good Vibrations, there's a theremin in there that goes, ooh, 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 ooh. That is a theremin. Also, if you've ever heard like a flying saucer noise in an old-timey movie where it went, ooh, again, that is probably a theremin. So we are going to create a pseudo-theremin in here, which again is sort of, it changes the notes when we don't touch. We're going to use the proximity sensor for that. That's the APDS9960. Now, that's going to be used to adjust the frequency or change the notes. It says down here that we should start with a low frequency of 65, which is a low C, and we're going to move up to a high frequency, which is a frequency of about 1976. Now, the potentiometer will be used to adjust the volume. Our students learned in a class exercise that we do that by manipulating the duty cycle, and again, we performed a similar task using a CPB. We're just translating that over to the Arduino Nano, but the code itself should work the same. Now, since our speakers can be plenty loud, I suggested setting the maximum value to 1/10 of the 32,760 value plus plenty loud. And here's a look at how this build works. Listen when you watch this to how the note changes. That's the frequency change, and it changes as my hand moves closer to the sensor or farther away from the sensor. And also listen to how the loudness changes as the potentiometer knob is turned. And now let's look at one way to code this. So first, let's import the modules that we need. That's going to be board, time, Neopixel, and PWM-IO, which is needed because we're going to be generating sound using PWM-IO audio. Now we also import analog in from the analog I/O module, and we use that to work with the potentiometer. Our students should know that a potentiometer is an analog input device. And we also need to import APDS9960. This is the proximity sensor that we worked with before, and we know that that comes from Adafruit_APDS9960.APDS9960. Now this is the exact same code that we used earlier to set up our proximity sensor. Nothing new here, but this is new. This is where we set up our PWM audio. Now this is audio that's generated using pulse width modulation. We're going to vary the frequency, and that's going to create different tones at different note sounds, and we're also going to change the volume and adjust that by setting the duty cycle, and we'll do that by getting input from our potentiometer. Now in order to generate PWM audio, we're going to create a PWM output object using the PWM out class, and we're going to call this tone. Now we pass into this the board.D4 value that just indicates that our speaker is hooked up to D4, and we're also going to set up the frequency so that we can vary it. We're going to vary that frequency based on our potentiometer reading, and that's going to change the tone. Now the volume is going to change by changing the duty cycle. Initially we're going to set that to a low volume. It's just going to be 25 for starters, but really what we're going to do is we're going to get this value from the potentiometer, so the initial value really doesn't matter. Now here's how we set up a potentiometer object to read. It's just this one line here. We're going to call a potentiometer. We read analog input using the analog in class, and we pass in board.A3. Again, I gave students information to use that as the pin to be able to connect your potentiometer to and do the reading. And again, you always want to make sure that you are plugging your potentiometer into 3.3 volt, not a higher voltage, because that will give you a wrong reading on the potentiometer. And we have our while true loop here, and the trickiest part of this build was probably calibrating things so that you get the right notes and you get the right sounds. So our proximity sensor, our students know from their exercise, has readings from 0 to 255. And even if you forgot that or you didn't have that in your notes, you could certainly go ahead and print out those values and find out what the different range is for the proximity sensor. Now we want to translate this into frequency values to play tones between 65 and 1976. We shared that on the previous slide. Now if we perform a little bit of math, we can scale 65 to 1976 down to 0 to 1911. So we just subtracted 65, so we can work with a number without any extra on the end there. So here we need to create what we called in class a scale calculation. So that's how many readings does it take for us to get in the range that we want for output. So if our max reading is 255 and our max output is 1991, which is after subtracting that 65, then we take 255 and divide it by 1991, and this gives us our scale value. Now in class, we also learned to be able to take the reading and compare it to the scale value. We take the current reading, divide it by that scale calculation we just did, and then add any adjustment in the end. Our adjustment is going to be the 65 we had up here. Now after we get the reading from 0 to 255, we divide it by the scale value, and then we add 65 to it. So this is going to give us something from roughly 65 through 1975 as a tone based on the proximity reading from 0 to 255. And if you're wondering if that's the case, just print out the value and you should see that that's what you come up with. So that frequency is our note, so we're going to put that in a value called freq, F-E-R-Q. Now to get the volume, we get the potentiometers dot value reading, and our students know from previous work with potentiometers that the maximum reading for a potentiometer is 65,520. Now what we want to do is we want to make sure that we max out around 32,076. I said that would be a good maximum value because the volume is pretty loud. So this is the calculation here, which will give us the appropriate volume. That's going to be a value that we push into the duty cycle. And so once we have our frequency and our volume, we just set these two values in the play a tone function. Now, frankly, the play a tone function only has 2 lines in here, so I could have put these 2 lines directly down below. We're not passing anything into this function, but by setting the tone object's frequency to .freq and the tone object's .duty cycle to volume, we set our note value and our volume value so we get our theremin to work just as advertised. So again, this was probably the most challenging example on the midterm, but hopefully you went through that and did a good job. And if you struggled, hopefully now that you try it out with this code here, you've got things working great and you see what's happening. So this was our midterm. Note that we have a no coder left behind policy in class. So if a student didn't do well, they could retake the exam after seeing these answers through this presentation, and their score on the retake will be multiplied by 0.7, and that will replace any earlier score they had. Now we do this so that hardworking students that really push themselves in a challenging class don't have to worry about having their grade torpedoed and being discouraged. It also really encourages students to go back and make sure that they know the things that they might have tripped up on initially. So we really want students at a university to take classes outside their comfort zone and to challenge themselves, and the best way to do this is to make sure that we don't discourage students by giving them really terrible grades if they push themselves and try to do something that they've never done before. You might not get top grades, but you'll still get a decent passing grade, and there are lots of additional ways to pad your grade throughout the course, like our weekly assignments and weekly online quizzes, and our students also get to be creative by completing 3 independent projects as well. So hopefully you did well, and even if you watch this, you don't need the no coder left behind policy, but if you did, hopefully you can go through this and really make sure that you understand how to solve all of the problems in our 8-question midterm. Keep at it. There's more big learning to come. Keep on hacking.